Okay, look at this, class has begun. So I just want to thank everybody for submitting a lot of questions. I actually got a lot more than I think I can answer in this, I don't know how long this will take. But it was super cool to see that even in these weird times, there's a little bit of normalcy and that I'm still a nerd, and a little bit of different, which is we kind of all have time to, I don't know, maybe talk to each other a little bit more or find out a little bit something, new. I've been reading a lot of history and, but then we've also been lounging. So I appreciate you guys taking the time to just kind of hang out. So I found out very quickly that this is gonna be backwards for you guys. So my visual aids don't have any words on them except for this title page, but because of the mirroring effect, I can't just write a bunch of stuff down. So that being said, I will go on through some of these visual aids, answer some of these questions. I have some notes in front of me to sort of help guide the conversation. I'm talking to myself, but help guide my thoughts. But if you guys have anything that you guys listen to me talk and have a question, feel free to just write something. I'll see it come up. But I wanted to start off with a really simple one and also a little bit of nepotism. This question comes from a girl named Rachel Y. So it's funny because I think Rach, which the joke is that's my sister, she asked this question as a joke, and I think it's funny because she's lived with me her whole life, and now we both live in Los Angeles, and I feel like she should really already know the answer to this question, but her question is, what is rocket? And her real question are, what are rockets and what do they do? Rach, I feel like I failed you if you've lived with me for this long and you don't know the answer to this question, but I think it's a good one to get us started. So I'm gonna start off talking about rockets in their commercial form. So not stomp rockets, not model rockets you can buy at the store. There's a lot of great tutorials on those, and I just feel like that has been an answered question, but I think the commercial side of rocketry is something that is my whole world, but much like commercial airline industry, not everyone's super familiar with it. So I wanted to start off with this drawing. So this is a 2-stage rocket. So the idea, I'm gonna hold it up actually above my head right now so you guys can see it beyond the comments. So yeah, Rachel, I know you said it was a joke, but now I'm gonna answer it. So this is, also pardon my nails. My salon's closed. Paige, if you're watching, we're gonna go get our nails done after this. So first stage is this body right here. A lot of rockets are first, single stage rockets. Those don't go as high because they don't have as much mass of propellant to launch large payloads, and we'll get to all that terminology soon, but this is called the first stage. This is actually called a second stage, and it's the idea that once you're high enough, you can separate these two, and the second stage will continue to boost you up higher and higher above the earth. And so the reason that I actually drew the engines or rocket engines on the bottom of these different sizes is because you can actually optimize engines to perform differently under the pressure, normal pressure of air on the surface of the earth versus up in space. So the idea is that rockets lower to the ground, when you're using them lower to the ground, their nozzle has to be smaller to get the perfect combustion, or as close to perfect combustion as you can get. But when you get higher up into space, you can actually use a bigger nozzle and get better performance. So 2 stages, first stage, second stage. Choose your own adventure starts here. So when you get to the top, depending on what you're launching, the top of your rocket may look differently. So for those of you who are colleagues, or for those of you who are fans of SpaceX, you can kind of tell that these might look a little bit familiar because they're similarly drawn to what SpaceX has. The bottom one here is a fairing. The idea is that a fairing can launch a satellite. The fairing is the clamshell part on the outside. So the idea is that if you just stuck a satellite on top, the wind resistance and friction from the wind as you're launching upwards would just tear it apart. So you have to cover it with this clamshell called a fairing. So I've sort of drawn this is what a fairing looks like. It's a half of one, and then this is what it would be like on the inside. So it's encapsulated by the fairing, and you have your little satellite sitting there at the bottom. And in reality, obviously, you go this way. So The other option is a capsule, and this is if you're launching, for instance, cargo to the International Space Station or people. So the Apollo capsule, the Gemini capsule, the Mercury capsule, this is sort of reminiscent of a Dragon capsule. And the idea here is that this is where you put people. Sometimes you have something called unpressurized cargo, which is like stuff that doesn't need all the protection that the people or the cargo do, but like, I don't know, boxes of stuff that are already protected or things you're gonna dump later. And so that's the idea of a rocket. So here, like, you can kind of see where this right here is just tubes with propellant in them. This is like stuff, right? So you need all of this in order to launch these smaller components and pieces. And the idea here is that the Tchaikovsky rocket equation is such that, like, if you have a heavy payload, you need a lot more propellant to launch it into space. But if you need a lot more propellant, it means you need a bigger first stage. And if you need a bigger first stage, that means it's gonna weigh more, which means you need more propellant. So you can see that, like, you very quickly enter this cycle of, like, we need more propellant because it's heavier, but we need more propellant because it's heavier. And that's why rocket's really hard. So it is interesting when you think of, like, engineering. You have people who build bridges. They are stationary. They are meant to carry some sort of load, and then they stay put, and that's all you want them to do. Like, the next sort of level of engineering, I'm not saying level of, like, difficulty, right? Like, I can't design a bridge, but the next level of difficulty in terms of, like, mechanics are if you add motion, right? So like a car, it has to be stable, it has to be sturdy, it has to be reliable, it has to go. But they don't really have to worry about weight as much, unless maybe you're a race car and you're trying to optimize for that. But the idea is, like, you can kind of build a car from the size of a Prius to a Hummer and it'll still go. But then rockets are kind of where you need not only to be able to go, but you have to be able to be light enough to carry the most stuff you can. And that's where the efficiency numbers come in, which is important from the business side of, like, how much stuff can you launch for as little material cost and, you know, all that stuff. But that's what makes rockets really hard, is it's not just about, like, the up, it's about, you know, how much stuff can you get every time you go up, and can you make a business around that. Yeah, so that is your, like, intro to Rocket 101. I know Rach said that was a joke, but it is actually a really fundamental question that I think a lot of people miss why that's important. Cool, thank you, Rachel. So the next question I got was from Katie, and it was about kind of like the life cycle of a rocket. And I chose to answer this question more from the, like, how do we go from factory floor to like space? And the idea here is that for SpaceX, it is more of a cycle because we reuse and relaunch our rockets. But in, like, traditional rocketry back, you know, as early as the 60s, it was a one-shot thing, right? So it was like a linear line. Now it's a circle. So I drew this diagram to help us out. Okay, so this line is really funny because I was talking to my roommate, Kate, which I think she's on. Hi, Kate. This is, like, her job. And the arrow back and forth is this idea that, like, we build stuff and we test it and we test it again. And then we, you know, put other things together and make subsystems. And then we keep doing that until we have a rocket. And so this idea, okay, the idea here is that, like, this is where you get something, what we call, like, a subsystem, which in this case, this is like a rocket engine subsystem. So the propulsion side of things. It's not just propulsion, you have structures, like the tube that is the rocket, you have the payload and the fairing on the top, or the capsule on the top, you have the software for a rocket, which is more of what I work on. You have all the analysis behind every launch about, like, where do we want to go and how do we want to get there, which is also kind of my job. But anyway, you get to this point where then finally you have, like, all the components are in the same room, or they're really, you know, integrate. And usually we integrate, which is like a fancy word for put everything together, in Florida at our launch site, or in Vandenberg, which is another launch site in California. And so you can see here that like you got all the pieces, you need to choose your adventure, fairing, or capsule, and then you've got your rocket first stage and second stage. And what actually I didn't draw is that in order to connect the two, you use the term, it's called an interstage, which is a very obvious term that connects the two. And so once you get to the point where you're like, okay, everything's in the same place, let's put it together, you do it and you launch. And then we land, right? So this is like a booster landing. You can see its little top hat, which is like the inner stage, and your little grid fins, which is what we use to guide the rocket to the ground. But then like the real mission, the whole point is to go to space. And so you can see here that we got, our satellites into orbit and we've made some money. And then at SpaceX, we land, we do some component checks. We make sure everything's still working. We replace things that may not be. And then we do it all again. So the key thing about this sort of cycle is, and like I'm, an employee of SpaceX, and I'm not at all speaking on behalf of SpaceX now. So please, no questions that I can't answer. But the idea here is that it is becoming more of a closed cycle in rocketry, to sort of like have that full closed loop. And it's become really, really cool to see the ways in which the industry as a whole is being pushed in that direction, right? Like every time in our industry we see, a new rocket company come online, or a new investment company invest in another rocket company or rocket technology, like they're no longer asking like how much can it lift to orbit, which is our like lingo for being like how much can it take to space. We also ask like, is it renewable, and is it something where you can recycle your rockets or land them again and use them again? Is it a good business model? So it is really interesting. The analogy that's used a lot is, what would plane tickets cost if your plane from, let's say, like LAX to CMH, home to Columbus for me, how much would your plane ticket cost if you had to like throw away the plane at the end of the flight? Like millions of dollars. So the reason that rockets have been not privatized earlier is because of that barrier to entry for just how expensive it is. And so now that we live in a world where we have the technology to recycle and reuse, it is allowing other customers, other payload satellite operators, countries that may not have been able to afford satellites before, to actually join the market. So it's a pretty cool, update to this industry, and it's why it's such an exciting time to be in rocket science and the business of rockets right now. So when I was thinking about a lot of questions came up about like who is the GOAT of all rockets, or what is the GOAT of all rockets, being the greatest of all time. I think I'd be remiss to say the Falcon isn't a feat of technology, but that's kind of like saying like who's the current best. But if we're gonna look back and really pay homage to all the scientists that came before us in the rocket industry, the Saturn V is like far and away the epitome of what it meant to be a rocket scientist in like the heyday early days, which I'm so thankful for. Kind of like that's coming back, that inspiration has been there forever, and we finally have the technology to make rocket science cool again. Leia, did you just say I'm a feat of technology? Thank you. So what I did want to compare though is that, we have the Saturn V and we have the Falcon, but they have very different missions, right? So Saturn V launched people to the moon. Falcon 9 launches things into orbit. And there's a lot more rockets these days that launch things into orbit around the Earth than launch people to the moon. So I wanted to show a comparison. Picture number 3. So this is an example of like what it means to launch from Florida. So this is Florida, sorry if you're from Florida, but this is Florida. And you launch up, and this is where you're putting something into orbit around the Earth, okay? So it's this like, this is where the rocket goes, and then the first stage is this little loop here that comes back or lands at sea. That's what SpaceX does with our first stages. And remember, the first stage is that buddy, the big one. So then what happens is this first stage comes and lands on a boat or comes back and lands at Florida, but like your moneymaker, the satellite, keeps going into orbit, okay? So this is Earth. orbit around Earth. This is a drawing of what happens when you go to the moon. So you launch from Earth, and you can kind of think of it like maybe this way, I don't know, doesn't really matter. In space, there's no such thing as up. So you're gonna launch from Earth, you're gonna go around Earth, slingshot in this figure 8 around the moon, and then come back. And this is supposed to show you that when you launch, the moon is in a different position from when you get there, okay? So you're dealing with so many rotating things that when you launch, you actually need to, it's like, I don't know, I'm not very good with hand-eye coordination, but like, it's like passing a football to a player where he's going to be, not where he is when you throw it. Boom. Okay, sports. I miss sports. So what ends up happening is you launch earlier than when you want the moon to be there, and then by the time you get there, the moon is waiting for you. You go up and down, maybe you orbit the moon a couple times, and then you slingshot home, and you land in the water, and the moon goes on its merry way. Got it? Boom. Rocket science. So my day job involves these trajectories most of the time, and my grad school thesis was on these trajectories. And so hi Mom, I have done now both, and each one has its own level of, I mean, they're all difficult, but going to the moon's hard. Like I know we did it in the 60s. It's still not easy. It's not like physics got any easier since the 60s. So like lifting a lot of stuff, still hard. The Earth is still big and weighs a lot, and therefore has a strong gravitational pull, and therefore it is hard to get stuff into space. That being said, I don't know if you guys have seen any memes on like online where it's like, please just shoot me into the sun. Maybe you have a really bad day during this pandemic and you'd rather be shot into the sun than, you know, be at home another day. Fun fact, it is more difficult to shoot yourself into the sun than it is to shoot yourself out of the solar system. Might sound super counterintuitive, but the idea here is that the trajectory you need to fly into the sun means it's really difficult. So the Earth, Caitlin, where are those ping pong balls? Not prepared. The Earth and the sun, Earth is rotating around, right? Actually, I'm just gonna do it this way because like I said, there's no up in space. And in order to fall into the sun, which is essentially what you're doing, you're letting the sun pull you in, you have to slow down your orbit around the sun to the point where you can fall in. That means you have to, the Earth is rotating around the sun about 30 kilometers per second. That means you have to go negative 30 kilometers per second. Caitlin, are you coming with the ping pong balls? Oh, I think she was going to get them right now. That means that you have to slow down negative 30 kilometers per second to allow yourself to cancel out the Earth's rotational speed. And so it's like it's like momentum, right? Like if you have momentum and you're in the air and you brake really hard in your car, you like fly forward, right? Same thing is if you have momentum from orbiting the sun, you have to slow it down. So then you have to go negative 30 kilometers per second, which slows you down, cancels out, and then you can fall into the sun. Contrast that with, it only takes 11 kilometers per second of speed to escape the solar system altogether. So it's almost a 3x difference, where it's 3 times the velocity needed to slow down to fall into the sun. So, yes! Here you go. Yes, thank you. Okay, I don't know how many more things I'll do with orbits, but yeah, so the idea is that if you're rotating around, this is 30 kilometers per second around the sun, you have to cancel that out. So it's like this idea of like just kind of stopping, because that's what happens when you cancel out your momentum, and then the sun pulls you in. Versus if you lose a third of that and you're only going 11 kilometers per second and it's slower, then you can, wait, that would have been really cool if I had done this the first time, but like, then you're out of the solar system. Cheesy. Anyway, so that's some mechanics. So if you ever see a meme that's like, shoot me into the sun, you can clap back and be like, that's actually harder than leaving the solar system. Or you don't have to do that. That sounds like a very me thing to do. Yeah, so a little more rock. That's like orbital mechanics. So we are shooting up in terms of difficulty level here. Oh, okay. So Michaela wrote, how do you move negative kilometers per second? So this is a really good, this is like a really good question. So when we think of like a graph, right, you have like your axes, you have positive x and negative x and positive y and negative y. So negative speed just means you're going in the opposite direction. So if the Earth at some point in orbit, oh, I threw my ping pong ball. Damn it. Come here, the other one go. If you are moving this way, 30 kilometers per second, the idea that you're going negative 30 kilometers means you're just going the opposite way. And so what happens is if you are going around the Earth and you're a little satellite, or the Earth around the sun, and you're 30 kilometers a second momentum, you need to cancel that out by going the opposite way, 30 kilometers per second. Does that make sense? It's all about like relativity. What direction are you looking at? What direction's positive? What direction's negative? Really good question. I think I don't think I use the term, but the term delta V, which stands for delta velocity, that is a big term in like orbital mechanics. And so when I say like you need 30 kilometers delta V, that's what that means. Cool. Good, Michaela, that helped. Awesome. Great. So there you go. There's your like integrating some memes into our rocket scientist. So another question was, what's the next big thing in propulsion? This was from Kyle. Kyle, haven't heard from you in a long time. It's nice to stay in touch. I kind of expanded this question to like what's next in spaceflight, because like propulsion wise, I'm not a propulsion engineer. I know that like nuclear propulsion has always been a big hot topic. Ion propulsion, these are all things that we use in space, but we don't use like ion engines or nuclear engines to like launch off the ground. We still use the traditional rocket engine with fire. But the idea here is that like spaceflight in general, you know, there's a lot of technology that we need to improve in order to make going to Mars easier. Material science improvements. We need, you know, better materials to be making things out of. And that's not just like a quality thing, that's like a brand new material. Like we need something that is light because heavy things are hard to launch. We need, and that's like, you know, storage containers, rocket material. What are we building rockets out of? That means things that can protect us from radiation. Right now, we live on Earth in the protection of the radiation belts, the Van Allen belts that are always around the Earth from our magnetic field. We don't get that luxury in space, so you need to be protected from the radiation from the sun. So materials that can do that but are also light, that is the like, what's that word? The thing you really need in order to go to space, in order to go to Mars and become a Mars-faring civilization. The other thing that we really need is, you know, advancements in computers. The better computer technology, the more you can automate things, the less you rely on humans to make good decisions. I know everyone thinks of like 2001: A Space Odyssey and HAL taking over the rocket. If you haven't seen, or the space station, if you haven't seen 2001, recommend it. But everyone's minds when I say, you know, we need better computers, always go to like the AI, very Hollywood type thing. That's not what I'm talking about. I'm more talking about just like the more we can automate things and make it easier for humans to live in space or live on Mars and have computers take care of the rest of our daily lives, like planting or growing or monitoring crops, or making sure that, you know, like a smart home, think of it like that, right? Like if a hole pops in your, if you guys have ever seen The Martian, the movie, if your hole pops in your habitat, like there's no air on Mars or the moon to like help you. It's also very cold, so you need temperature control, all that kind of stuff. Anything to make it easier for us to just kind of try and survive, that'll be a big deal. So thanks, Kyle, for that question. So the rest of the questions that I have, let's see, we're about 25 minutes in. I'm gonna jump to a section, a little bit quirkier questions. This is just like generically about outer space. And so Nick P asked me a question about what's the quirkiest thing I've ever learned about space. So this is a fun fact that blew my mind, and I had like an existential crisis afterwards, so buckle up. So the Big Bang, that was the beginning of our universe as we know it. It's the last thing we can see with telescopes looking back, because first off, the really cool fun fact is that telescopes are time machines. When we look at the light from stars, it's taken millions, if not billions of years to reach us, which means we are seeing the light from a star as it was millions of years ago, not as it is right now. So with telescopes, we've been able to look back in time and see the Big Bang was, we know enough about science and all this stuff. The Big Bang is a thing. Well, what I learned about the Big Bang that I didn't appreciate before was that when the Big Bang happened, like particles went everywhere. And I'm not talking like oxygen and hydrogen and carbon. I'm talking like barely electrons, not even protons and neutrons. And as the universe cooled down, things started to coalesce. And so you had electrons that were losing their negativity and making protons, and then you had an atom, and then you had hydrogen, and then you had, whatever, and on and on and on. Well, what I learned was the matter dispersed unevenly, right? So it wasn't like everything was equally spread out, because if that had been the case, things would have just kept moving away from each other, and we never would have coalesced, okay? But it also wasn't too clumped. If the Big Bang had happened and things were too clumped together, it would have immediately shrunk back down to the tiny, tiny thing that was before the Big Bang, and might have exploded again, it might not have exploded at all. And so when the Big Bang happened, it dispersed at just the right unevenness. It was like the Goldilocks, right? So it was like the Goldilocks of the Big Bang, and the way that the atoms and molecules spread out and then coalesced over time, and then formed planets, and then formed, solar systems, and then formed galaxies, led us to where we are today. And that, think about it. If an atom was somewhere else after the Big Bang, maybe humans don't exist. Or if it was just differently dispersed, maybe, it's just crazy. It's kind of like this idea of, how did we get to where we are and when we are? This idea of why humans evolved at the pace that they did. Yeah, it blows my mind. This is the stuff where I remember as a child being 7, 8, 9 years old and trying to solve these mysteries in my head at night before going to sleep. And that's probably why I'm very uptight as a person. So anyway, yeah, that was a fact that I remember just kind of hitting me pretty hard and being like, wow, we actually see the Goldilocks principle a lot in the universe. The just right, Earth is at just the right distance from the sun, that water doesn't boil off or doesn't instantly freeze, and we can thrive on it, and we can deal with temperature swings in this range, and that happens to be the temperature swings the Earth experiences as a whole. Lots of things in science in general, where we are very well evolved for this specific range of things. And it is why climate change is an issue that we have to remember is not just about okay, it's going to be a little warmer. It's that, what does that do to life in general that has been targeted to be evolved to this particular range of external factors in the world? And what does that change? What does that throw off? Where does the balance, where does the teeter-totter, the very Goldilocks zone change? How does that affect us? So yeah, that was probably the quirkiest question, and it's one of those things where it's ever since that fun fact about Goldilocks, I see it pop up in a lot of different areas of science. Nick P also asked, what's the scariest thing I ever learned about the universe? I think I am most scared about living and dying and not ever knowing if we are neighbors to some other celestial life form. For those of you who have seen Contact with Matthew McConaughey and, oh no, she was not Helen Hunt. Someone help me out. Who? Blonde from Contact. She's like the star. Oh no. Anyway, the movie Contact, originally a book by Carl Sagan. Excellent movie. I always wanted to be Ellie Arroway, which is the character's name. What is it? Jodie Foster. So sorry, Jodie, if you're tuned in. God, what a brain fart. And then, oh, hey, I forgot to show you one more drawing. Let's see. This is a comparison. So we talked about like the GOAT of rockets. Here are my favorites. Okay, it's like a police lineup. This is meters. Starship is a meters program, or an SI units program, meaning that we deal with meters and all of the non-silly English units system. We don't do it. So hop on board. We're talking in meters. Thank you, Jodie Foster. Jodie Foster. Mom, Dad, you're probably sitting next to each other. Thank you. Okay, my favorite rockets. This one. This is the Mercury Atlas. It's what launched John Glenn, little baby rocket. Can you imagine sitting in that tiny, that's where John Glenn sat and went into space. Amazing. Falcon 9, she's a beast. Very tall, skinny noodle. Saturn V launched people to the moon. Come on, the GOAT. And then the shuttle. So the first rocket launch I ever saw was a space shuttle launch, the Discovery, on July 4th, 2006. Got delayed a couple days. It was the only 4th of July launch in the history of the shuttle program. Pretty wild. And then a mentor of mine named Kurt Brown used to be the commander of those shuttles and actually was the commander on the shuttle where John Glenn, as a 77-year-old man, went back into space to be a guinea pig for us as a sort of human test subject as an old man. Pretty wild life I've lived to say that Kurt is a good mentor of mine and was like a 6-time shuttle commander and kind of bros with John Glenn. Wild. So what a cool opportunity to chat with you guys today. I got a lot more, oh my gosh, sorry, hold on. Coffee. I like to talk, but clearly need a little water. Well, whatever, liquid. This was a lot of fun. I hope to maybe do this again sometime if you guys really liked it. I think a half hour is probably a good goal. I don't want to bore you or anything. I actually had more notes about other questions. I think an area that I really want to talk about because it aligns with my, oh my gosh. It's not Corona, I promise. Caitlin and Dawn, my 2 lovely roommates. But my minor was international relations, or international studies, security and intelligence in college. And so I got a lot of questions from some friends about like issues with foreign relations in spaceflight. We had a really good relationship, ironically, with the Soviet Union in space during the Cold War. There's a lot of stories about that are really cool. There's a lot of issues in our current day and age about space junk in orbit. What does that mean? What is it? What does it mean? As well as some of the like health and human sciences part of things. So I think if I'm going to do another one, I think that's kind of what I'll do is maybe pivot away from just the like cold hard facts about rockets and trajectories to maybe a little more of the human issues, the international relations, the global health, the, you know, what have we learned from the space program and NASA as it stands right now? A lot of friends, not just strangers, a lot of friends will come up to me and say, I didn't realize NASA was a thing anymore. And so let's debunk that. And maybe we'll talk a little bit about Mars. I got a couple of questions about that too that kind of didn't fit into my lecture. So awesome. Yeah? Have fun? Do we do good? The lighting's good. My makeup looks really good right now in this light. Really happy with the California skies the way they are. And awesome. Okay, y'all, I will talk to you soon. Be safe, take care of each other, and send me your questions. We'll do this again. All right, love you guys. Bye.